Welcome to the supplemental lecture on thermochemistry for Jamie Ansell's Chemistry 161 class. In this supplemental lecture, we'll be looking at two major topics, Hess's law of summation and standard enthalpies of formation. We'll then use standard enthalpies of formation to calculate enthalpies for an entire chemical reaction. Hess's law allows us to look at chemical reactions that have a difficult enthalpy of reaction to measure. But if a reaction occurs in multiple steps and we're able to measure those individual enthalpies, we can sum up the individual steps' enthalpies to find the enthalpy of the entire chemical reaction. Mathematically, it looks like this, where we have two steps to a chemical reaction, H2 and H3. When we add them together, we're able to calculate the enthalpy for the overall reaction, H1. An example of this can be seen in this graphic, where methane and oxygen gas will overall react to produce carbon dioxide and water. This overall reaction is made of two individual steps, H2, which is exothermic, and H3, also exothermic. The products of H2 will undergo one more chemical change to make the final products of our chemical reaction. Since our H1 reaction occurs in two steps, we can calculate the enthalpy of that reaction by adding the enthalpies of the individual steps. H2 plus H3 gives us our overall enthalpy of reaction, H1. Hess's law problems are sometimes considered puzzles because there are multiple pieces that we need to manipulate to get an overall picture. To do these types of problems, we'll begin by looking at a thermochemical equation that occurs over a series of steps, paying special attention to the states of matter present. We'll then manipulate the equations and then add up the enthalpies of the individual steps to find the enthalpy for the overall equation. By manipulate, I mean that we can reverse a chemical reaction, turn reactants into products and products into reactants. And when we reverse a reaction or flip it, we change the sign of the enthalpy from either exothermic to endothermic or endothermic to exothermic. We can also change the coefficients of our thermochemical equation. We can multiply by 2, by 3, or even cut them in half. Whatever we do to the coefficients, we also do to the enthalpy of that reaction. Once we've modified our chemical reactions by reversing or by multiplying, we'll then add up the individual steps, cancel out any spectators that have the same state of matter in reactants and products, and then add the enthalpies of our individual steps to find the overall enthalpy. Here's an example. Say we're trying to find the enthalpy of an overall chemical reaction between carbon monoxide and nitrogen monoxide to produce 1 mole of carbon dioxide and half a mole of nitrogen. One thing you may notice that's different about a thermochemical equation is that coefficients can be fractional. Now this reaction happens over two steps, equation A and equation B. I'll begin by looking at equation A and B and seeing what matches about our overall equation. I notice that carbon monoxide is a reactant in both equation A and the overall reaction, and carbon dioxide is a product in both reactions. Equation B, on the other hand, has nitrogen in the reactants, but our overall reaction has nitrogen in the products. I'm going to begin by modifying equation B. I'm going to flip it and divide all of the coefficients in half so they match my overall equation. That'll then give me half a mole of nitrogen, half a mole of oxygen, and 1 mole of nitrogen monoxide from a modified equation B. I'll rewrite the equations so you can see what they look like after the modifications. Equation A doesn't change, so I rewrite it in the same way. But equation B has been reversed, reactants becoming products, and all the coefficients have been divided in half. For equation B that we've modified, we have nitrogen monoxide as a reactant, half a mole of nitrogen and half a mole of oxygen as a product. There's a spectator in each reaction that we can cancel out before we add them together, and that's the half a mole of oxygen gas in both reactants and products. We'll then rewrite our equation, adding our equation A and equation B together. Carbon monoxide and nitrogen monoxide are both reactants, and carbon dioxide and half a mole of nitrogen is a product. Because we just add our individual equations together to get the overall reaction, we're going to do the same thing to the enthalpies. The enthalpy for equation A remains unchanged because we didn't modify equation A, but equation B's enthalpy is going to be divided in half and the sign will be changed. So because we flipped our reaction, the enthalpy for B became negative And because we divided all the coefficients by 2, we also divided the enthalpy by 2. Adding up equation A and our modified equation B gives us our overall enthalpy of reaction of negative 373.3 kilojoules. To review this Hess's law problem, we began by looking at equation A and equation B and seeing how they matched our overall reaction. We then modified equation B by flipping it and dividing the coefficients by half so that they would match our overall equation. We then added equation A and equation B together and added their enthalpies as well. We canceled out the spectator of half a mole of oxygen since it occurs in both the reactants and the products. We now know the overall enthalpy of our chemical reaction is negative 373.3 kilojoules. Here's another example. Thermochemical equations can be written for both exothermic reactions and endothermic reactions, or chemical changes and physical changes. We'll be looking at physical changes of water, specifically vaporization and fusion. The goal of this question is to write a thermochemical equation for each of the following changes, then calculate the heat absorbed or released when water freezes. Not 1 mole of water, but 3.5. Remember that fusion is melting, which means the opposite of fusion would be freezing. Here's the equation for fusion: solid water turning into liquid water. If I flip the reaction, I can look at the freezing change of water, going from liquid to solid. Because we flipped our reaction of fusion, we also changed the sign of the enthalpy. Positive 6.01 kilojoules per mole becomes negative 6.01 kilojoules per mole. Energy is absorbed when water melts, and it's released when water freezes. So to do this thermochemical problem, we'll begin by writing down our 3.5 moles of water that we want to freeze at 0 degrees Celsius. We'll then use the enthalpy of freezing to convert moles of water into kilojoules. If we had 1 mole of water freezing, 6.01 kilojoules would be released, but we have 3.5. Moles of water will cancel out, and overall, I'll be able to figure out that 3.5 moles of water freezing releases 21 kilojoules of heat energy. So to review, we took our fusion equation and flipped it to figure out what the enthalpy of freezing would be. We then applied that to a thermochemical stoichiometry problem, converting moles of water that freeze into heat that's released when that water does freeze. Standard thermochemical conditions are common conditions that are usually used for thermochemical reactions. You may recall that when we looked at gases, we looked at STP, or standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. Standard thermochemical conditions are slightly different, and they only apply to thermochemical reactions. Pressure is the same, but the temperature is different. When a chemical reaction is done at standard thermochemical conditions, or STC, the enthalpy of that reaction is denoted with a little zero, or not symbol. Here are 2 examples. This enthalpy of combustion happens at STC. I can see that because of the little not symbol. And the overall enthalpy of reaction that's listed also occurs at STC. One specific type of enthalpy is called a standard enthalpy of formation. We say standard because it occurs at STC, and we use a little not symbol to indicate that formation happens at 25 degrees Celsius and 1 atmosphere of pressure. Enthalpy of formation is the energy associated with 1 mole of a substance being formed from its pure elements at standard temperature and at standard thermochemical conditions, STC. Here's a list of standard enthalpies of formation for many different substances. These are definitions that from the elements of our compounds, when they are added together, energy is either released or absorbed as the compound forms. For pure elements, they are not formed from other elements, they are just themselves. So the enthalpy of formation of a pure element is always 0. We'll look at 2 compounds, water. So when water vapor forms, 1 mole of it, 1 mole of hydrogen gas will react with half a mole of oxygen to make 1 mole of water in a gas phase. The enthalpy of formation is circled here in the table for water in a gas form. When 1 mole of water forms as a gas, negative 241.8 kilojoules of mole is associated with that formation. Or when 1 mole of water is produced in a gas form, 241.8 kilojoules are released. It's important to note that the enthalpy of formation of gaseous water is different than the enthalpy of formation of liquid water. It's also different than the enthalpy of formation of solid water, since gas, liquid, and solid have different heats associated with them, as the molecules move at different rates. States of matter are very important for standard enthalpies of formation. The standard enthalpy of formation of liquid water is negative 285.8 kilojoules per mole, slightly different than the standard enthalpy of formation of gaseous water. We can calculate the enthalpy of formation of a chemical reaction by examining the enthalpy of formation of all of the elements and compounds involved in the chemical reaction. So if our chemical reaction involves making compounds, we can view this change as breaking the compounds down into elements and then taking those pure elements and reforming the products. So the enthalpy of formations can be used to break down compounds into their elements and then elements into compounds. This can be seen here where we have our reactants. The reactants we can think of as decomposing into their pure element form, or negative enthalpy of formation. Then if we take the pure elements and form them into the products, we have a positive enthalpy formation. So when we look at enthalpy of an overall reaction, first we're going to break down the compounds in our reactants with their enthalpy of formations, then take their pure elements and form them into new compounds. The overall enthalpy of our reaction is our initial compared to our final. The products minus the reactants is the overall enthalpy of our reaction. But we can use the enthalpy of formations of our reactants and products to calculate this overall enthalpy. Here's an example. Mathematically, using enthalpies of formation to find enthalpy of a whole reaction looks like this, where the enthalpy of our whole reaction is equal to the sum of all of our enthalpy of formation of the products minus the enthalpy of the reactants. And we're breaking down the enthalpy, or breaking down our reactants, which is why it's a negative symbol, into their pure elements, and then combining them together to make products. M and N are the moles of our reactants and our products. Here's that graphic one more time. So the formation of our products from the pure elements is always going to be positive, which is why we're summing up positive numbers. And we're subtracting or adding negative values because we're breaking down or decomposing our reactants. The overall enthalpy of our reaction is breaking down the reactants into its pure elements and then forming them together into their products. Let's look at an example. We're going to calculate the enthalpy of this reaction at STC from the enthalpies of formations. We have 1 mole of nitrogen monoxide reacting with half a mole of oxygen gas to make 1 mole of nitrogen dioxide. And we're going to calculate the overall enthalpy of this reaction. We're going to apply this mathematical formula to our chemical reaction. Okay. So when we look at products, we only have one. We have one product right here, nitrogen dioxide. We're going to take the 1 mole, our coefficient, and multiply by the enthalpy of formation of nitrogen dioxide, which we'll look up in a table. We'll then subtract the sum of all the reactants, or 1 mole of nitrogen monoxide times its enthalpy of formation, plus half a mole of oxygen times its enthalpy of formation. So the mole amounts match our coefficients, and the enthalpies of formations we'll look up in a table. Our products always minus our reactants. Final always minus initial to find an overall enthalpy of our reaction. Let's plug in our numbers. I used a table to look up the enthalpy of formation of nitrogen dioxide. It's 33.2 kilojoules per mole. And then we're going to subtract our reactants. Nitrogen monoxide has an enthalpy of formation of 90.3 kilojoules per mole. And oxygen, since it's a pure element, has an enthalpy of formation of 0. If I multiply all my mole amounts by my kilojoules, I'm able to calculate the overall enthalpy of reaction of negative 57.1 kilojoules. So breaking the reactants down into its pure elements and then forming them again into products is overall an exothermic reaction, releasing 57.1 kilojoules per mole every time this reaction occurs.